Okay, so any theory of how the solar system was formed has to account for these regularities, right? The fact that the solar system is flat, that there is that counterclockwise twist. There are two groups of planets. Those close to the sun are small in size and mass, relatively speaking, but they are dense, while Jovian planets at greater distance from the sun, beyond, say, 5 astronomical units, they tend to be large, both in diameter and mass, but they have low density compared to terrestrial planets. So any theory of the formation of the solar system has to account for those observations. And nowadays, there is basically a prevailing scenario which gives pretty good account for what is being observed, although there are some details that are still not quite well explained. So this is the story that you remember from us discussing the star formation, right? So there was a part of a large molecular cloud with clumps that might have been created by a nearby supernova explosion. The shock wave from the explosion might have compressed parts of the cloud, and some of those dense clumps started collapsing. Okay, and the clump was initially spinning, and as it contracted, it started to flatten. The parts that were moving in a plane perpendicular to the spin axis could not fall as easily as in the direction parallel to the spin axis. So this so-called accretion disk was formed. Things were happening here that I will discuss in a moment in more detail, but eventually what was the result was we had the star at the center, our sun, and planets revolving around it. So the flatness of the solar system, this counterclockwise twist, are naturally explained by this scenario where the clump was spinning in a particular direction. The conservation of angular momentum tells us that that spin direction has to be unchanged. So the entire solar system is retaining overall spinning motion in the original clump that started collapsing. The flatness is again explained naturally by flattening of this clump as it contracted, flattening in the direction of a spin axis. So this collapsing nebula hypothesis can account for these aspects that we observe in the rotation of the solar system. So here is an artist's image of how this accretion disk around sun just coming onto the main sequence looked like. And I've denoted here a line, so-called frost line or snow line or ice line, which in the case of the solar system has a radius of about 5 astronomical units, just about the radius of Jupiter's orbit. And what does this line represent? Well, the temperatures within the frost line are higher than minus 120 degrees centigrade. And the temperatures beyond the frost line are lower than minus 120 degrees centigrade. Okay? So why is that important? Well, there is a property of substances called condensation temperature, which is the temperature at which a particular material forms a solid. And it depends on pressure. The higher the pressure, the higher the temperature at which material solidifies. The lower external pressure, the lower the temperature is. And you should keep in mind that in space, the pressure is 0. So let's look at this so-called condensation sequence. Here I'm listing material, the relative abundance of material in the solar nebula by mass, and the condensation temperature. For metals like iron, nickel, and aluminum, which constitute by mass only 0.2% of the solar nebula, the condensation temperature ranges between 1,000 and 1,600 degrees Kelvin. Various minerals, they form about 4% by mass of the material in the nebula. Their condensation temperature, the temperature where they become solid under the nearly 0 external pressure, is between 500 and 1,300 K. Okay? Now, water, methane, and ammonia, they constitute 1.4% of material in the solar nebula, but they can form solid particles at temperatures less than 150 degrees Kelvin, which is minus 120 degrees centigrade. So this is why this demarcation line, the frost line, which separates the temperature ranges between higher than minus 120 degrees centigrade and lower, is important. So you see, within the frost line, only metals and various minerals could form solid particles. Gases like water, methane, and ammonia could not. Okay? So they could form solid particles only beyond the frost line. Now you say, well, something is wrong here. I mean, I know that the temperature freezes at 0 degrees centigrade. Yes, but that's under the atmospheric pressure of 1 atmosphere. Because the pressure of our atmosphere is substantial, the condensation temperature is elevated. In 0 pressure conditions, like it existed in the solar nebula, water would freeze at much lower temperature, at minus 120 degrees centigrade. And then hydrogen and helium, which constitute 98% of the mass of the solar system, they do not condense at 0 pressure. Okay? So then terrestrial planets, those within the frost line, right, are composed of rocks and metals, because only those substances could solidify within the frost line. It doesn't mean that they could not solidify beyond the frost line. They could, of course. But beyond the frost line, we could have solid particles of water, ices, methane, and ammonia, right? And hydrogen and helium, they remained in the gas phase. So then what was happening is that small solid particles of one kind or another collided. It was very crowded in that stage in the accretion disk. Two particles would collide, and occasionally they would stick together, held together by so-called adhesion forces, which are electrical in nature, right? And they can be quite strong, these forces. For instance, if you have some dust on your car, you cannot remove it by driving very fast, hoping that the wind is just going to blow the dust away, right? Those particles are bound by adhesion forces to the paint quite strongly. The only way to remove them is to wipe them, to wash them away, okay? So those are the adhesion forces. And through this so-called accretion process, they were forming larger grains. And through this accretion process, larger bodies, so-called planetesimals, were formed, which ranged in sizes from 1 kilometer across to maybe 100 kilometers across. So the process, you could think of rolling a snowball on the snow. As you roll it, the adhesion now between the snowflakes piles on more and more snow, and your snowball grows in size, right? So these objects could grow in size via this accretion process. And these now larger bodies swept quite a bit of dust and small particles in the solar nebula. And as they were growing in mass, their gravity started to become important. And at some point, when the gravitational attraction that they exerted on surrounding bodies became significant, they grew up rapidly, forming what are called protoplanets, or planets to be. And then, when the sun, sort of just before it stepped on the main sequence and reached the state of hydrostatic equilibrium, it went through a turbulent phase, so-called T-Tauri phase, which was accompanied by very strong solar wind that just blew out anything that wasn't tight, so to speak. It just cleared out the dust and gas that was still dispersed between the planets, and the newborn solar system was revealed. Okay? So this entire process of the formation of the solar system may have taken, based on the mass of the sun. We can find out how long it takes for a protostar to contract and form a star of sun's mass. This process may have lasted a few 100 million years and was completed about 4.6 billion years ago. So how do we know that? Well, we can do the radioactive dating of rocks. We also, understanding the solar physics, we can find out how long the sun has been shining from its mass and luminosity, and that can give us a pretty good idea how old the solar system is.